Yeah, thanks, Chris, and I'm really happy to be here. Thanks for inviting me. This afternoon, I'd like to give you a little bit of a grand overview of sort of my research area. And in recent years, I've been concerned quite a bit with hydrodynamical simulation of galaxy formation. So I'd like to give you a little bit of a personal view on this field, starting a bit with the history and setting this in context, discussing a bit the current state of this area, what are the successes and what are the challenges, and give you a bit of a personal maybe outlook on where I see some of the challenges and what we are going to see in the next couple of years. So lambda CDM is our cosmological model that we love and cherish, and it's giving us initial conditions that are precisely laid down. And I've been studying in my work mostly computational structure formation, where I took the initial conditions left behind by the Big Bang, which we constrain, of course, with the beautiful CMB observation and other cosmological probes to high precision, use them as initial conditions and then evolve it forward in time. And you all know that as far as the dark matter is concerned, we can carry this out with high precision. And these simulations have been instrumental, the dark matter only calculations, to, for example, tell us how many nonlinear objects of a given mass exist, the halo mass function, also the internal structure dark matter halos has been clarified. In fact, this is fairly interesting. If you zoom in one of these objects, you get this sea of dark matter substructures in halos. And from this image alone, you couldn't tell whether this is a galaxy cluster, a Milky Way system, or a dwarf galaxy. They all look the same. They are nearly scale invariant. Of course, once we are adding the baryons, this will change. The scale invariance, the near scale invariance of these systems will go away. So as far as dark matter is concerned, the problem is cold dark matter is kind of solved. Of course, the missing item here is that we don't actually know what the dark matter is in the end. We still explore other alternatives, but the vanilla candidate to this day is still a sort of WIMP-like particle, a massive, weakly interacting particle behaving as cold dark matter. And in that limit, we have very accurate simulation predictions, except that in principle, we don't yet know necessarily what is the structure of the smallest halo. So that was a somewhat unclear open issue until, I think, let's say recently, because there's new work by Jay Wang and Sonak Bosi and co-workers, and I was also involved in this, where we tried to address this with a series of extreme zoom calculations. And I just want to show you this here. This is a 500 megaparsec parent calculation, the original Millennium volume, just updated to the Planck cosmology, dark matter only, and then through a sequence of 8 zoom calculations, we've zoomed into objects trying to uncover in a gigantic cosmological volume the smallest dark matter halos that form. Those will be, for a canonical WIMP, about 100 GeV particle of Earth-sized dark matter halos. And in fact, we reach here now a mass resolution of 10 to the minus 11 solar masses, which I think is quite good, in a box that contains 10 to the 19 solar masses, right? So this is, I think, a tribute to what you can do these days in a truly multi-scale calculation. So this is an extreme zoom. Of course, the dark matter problem is comparatively simple. Still, doing such extreme zooms over 30 order of magnitudes is also numerically very hard. That's why this was requiring us also to change the simulation codes multiple times to actually reach the required accuracy. But at the end, we get a fairly interesting result, not fully unexpected, because the NFW, or rather Anasto profile, have been demonstrated before to match the dark matter profiles very well for much bigger halos. Now it turns out they also match to high accuracy, even the smallest dark matter halos that form. So the Earth mass dark matter halos are also matched to about 7% accuracy with the Anasto profile, so over these very large dynamic mass range in mass. More interesting is the concentration-mass relationship. This is something that has been explored a lot, and people have used this typically considered massive systems to write down empirical fits for the concentration-mass relationship. And when you extrapolate this to the thermal cutoff scale, 10 to the minus 6 solar masses, so sort of an Earth mass, where you expect the smallest halos in this canonical WIMP model, you see that these predictions are actually very different from what we find in the end. There was one theoretical model by Ludlow that describes precisely this finding, and that has sort of been confirmed. This is a model that relates the concentration of dark matter halos to the mass accretion history. It works astonishingly well, as you see here. It's matching the simulation results in the end very, very well. Why does it matter? Well, it matters for questions like dark matter annihilation. This concentration mass relation leads then to a correction of predictions for the annihilation flux by about a factor of 10 or so because of the subclumping. So now with this little side remark on the dark matter side of things, so this is a small update from that front, let me turn to the hydro simulations. Now this is something that has been, of course, been attempted really early on. So these are some old results from 15, 20 years ago almost, well, 15, 10 years ago. Attempts to simulate cosmological boxes with the baryonic physics included and then forming directly the galaxies. And one famous problem that surfaced immediately early on is the so-called overcooling catastrophe, how this has been termed, namely the fact that even in crappy resolution simulations, the gas will cool and condense in the dark matter halos, and there's nothing really that stops it. Typically, it will turn into stars. You predict star formation rates that are far higher than what's observed in the real universe. And predictions early, this is an early prediction for the cosmic star formation rate history. See here early data, and over prediction by a factor of 3 to 5 or so. If you increase the resolution, it gets worse, and you turn way more baryons into stars than you really expect. And predictions for the galaxy luminosity function, so 10 years ago, looked like something like this, right? Here is a Schechter function of the observed galaxy luminosity function. There's a very steep faint end in this hydro simulation. There's an excess at the bright end, and you don't fit the knee. So it could hardly be worse than that. So the shape was very bad. Complete failure, but, and if you go back to this history, you will see that nowadays, of course, we are doing much better. And I'll get to this, but here was an early attempt of a disk galaxy formation. And the disk is there at redshift 0, but it's actually pathetically small compared to the big spheroid that has also formed. And the rotation curve of this Milky Way-sized galaxy shoots up to 450 kilometers a second or so at the center, as quite unlike a flat rotation curve that you would expect for Milky Way. So also here, a strong failure. And that's because of the same problem. The baryons settled into the center, and you make an extremely massive bulge that shouldn't be there. If you look back in the recent decade, though, suddenly much more successful disk galaxy simulations appeared. Here are different examples: Scania-Pecco, Ruedes, Argels, and then more recently, further work Stinson, Aumer, Marinacci, Phil Hopkins. You see that these galaxies get quickly prettier over the years because they are rendered more nicely, but they also match the properties of the galaxies much, much better. And this is what we are currently at it. So this is our newest Arepo model, with a more resolved ISM model. And you see, if you put the dust planes on top, it looks much nicer and much closer to reality. And but this from a distance, you could mistake maybe for a real observed galaxy. So I think the progress here is kind of stunning over the course of 10 years. And so multiple groups are able to simulate hydrodynamically galaxies at that time. So that's quite remarkable. Why was there this progress? I think there are two fundamental reasons, and I don't want to dwell on all of them because there's a large shopping list of so-called feedback processes that fight the overcooling, that regulate star formation in a sense that we observe. And the two main culprits here are effects related to stellar evolution. So supernova explosions is a clear traditional energy source that we know is there. Stellar winds and also the radiation fields by massive stars, and black hole activity to quench the star formation massive systems. But this is only sort of the main contenders here. We think that there might be additional physics that's relevant relating to, for example, the radiation fields, radiation transfer, radiation pressure and dust, or non-thermal particle populations, cosmic rays, which I'll also later talk a little bit about more. Maybe MHD effects, magnetohydrodynamics plays a role as well. Or exotic physics, you find many speculations of what could curtail the star formation galaxies. And the other big issue, I think also, even though that's more debated, how relevant this is, I do think that the numerical methods themselves have become more accurate as well. Here we developed, for example, because of problems with the gadget code, which is a smooth particle hydrodynamics technique, which used to be very popular, but has a very noisy rendering of the hydrodynamics and also has problems in suppressing fluid instabilities from growing under certain conditions. We developed this moving mesh code, ARIPO, and here you see a comparison of a disk galaxy formation calculation where the same initial conditions was simulated with the same physics in this case, using two completely different hydrodynamical solvers. And in both cases, a disk system is formed, but you see very clearly that the moving mesh calculation seems to be making a bigger disk, a much less noisy density field. And these effects are there. The accuracy of these numerical methods differs substantially. And what's debated basically among the pundits here is whether this matters, because in the end, because of the uncertainties involved with these baryonic physics processes, which we have to often parameterize somehow semi-empirically or heuristically. And you can absorb maybe some of the errors in the codes in this parameterization. And I think this is partially true, but I think it's a dangerous road to go down. So I would ultimately like to have a predictive numerical solver where I can rely on an accurate solution of the underlying partial differential equation that we're trying to compute. So nowadays, with these improved codes, both also the SPH codes have also been improved. I don't think they're as good as the mesh codes still, but they are having improved a lot. And then different groups have now ran in the recent years very large volumes, cosmological volumes, where not only the dark matter was simulated, but baryons as well. And the most important physical processes regulating galaxy formation or determining it. That is radiative cooling, stellar star formation, and some feedback process related to star formation, some black hole growth, and some feedback process related to black hole growth. And here are some of the projects, Illustris, Horizon AGN, Magneticom, Eagle, and so on. These are some of the more well-known ones. It's not a complete list, and more recently, Illustris TNG, which I'll refer to a little bit more. And with Illustris, this was in 2014, we managed for the first time to reproduce the morphological mix of galaxies. I think this was an important first success that these calculation, even though that wasn't somehow put in, produced different shapes of galaxies, namely disk systems of roughly two arms, barred systems, pure disk system ellipticals, and then you can arrange that sort of as a two-uniform diagram. And also the morphological mix changes as a function of stellar mass, roughly like observed. So that was maybe the most important success here. The detailed properties and galaxies were partially successful too, but there were also discrepancies. And in particular, we still had two big galaxies. That's why in recent years we turned to the next generation Illustris model, again run with this moving mesh code. And this time the idea was to look at different volumes. So here is a 50 megaparsec box, TNG 50, 100 megaparsec box, and 300. With the idea being that due to computation limitations, we would like to address a fairly large volume at very good mass resolution to see the smallest galaxies. This you can't afford to do in these very large volumes. So the way out is to restrict your volume, then be content, for example, 50 megaparsec, and then you, however, don't see rare systems like rich galaxy clusters. But by overlapping these volumes with overlapping mass resolutions, again, then patch together a full consistent picture of all the objects that are there. That at least is the idea. But even, I should say, for cosmological applications, these 300 megaparsec volume is basically not large enough. The baryonic acoustic oscillations are basically hardly in there in this volume, and if, then only with a few modes. So that is one of the challenges to the future, to have still larger hydro simulations, because they're so humongously expensive. That's actually real difficulty. In fact, these TNG runs, for this we already needed a big supercomputer. This was run, this machine, a great computer in Stuttgart, and the TNG 50 calculation, I'll show you couple of results in a minute, consumed about 100 million CPU hours. So this is one of the most expensive runs in the field so far. So it's not a cheap way to do science, for sure. So, and unfortunately, And once you have done the calculation, it's also not easy to change it and do another one big problem. Just to give you a visual impression, here is a nice movie that Dylan Nelson rendered. The formation of a disk-like galaxy, in this case a small cutout from the TNG50 simulation box. What you see here in the background is the gas flow. Here's a redshift counter, which redshift 3.56-ish, and the other insets here, this is the dark matter backbone. Here are the stars, and this is, I forgot what this is, the bottom right. Should also be the gas. Huh? Shai, do you remember what this is?
I think it's just the gas and zoomed in. Yeah.
Zoomed in, I guess. Yeah, it should also be the gas. Right, but we are approaching. You see how wild actually the gas flows are. Is a multi-phase gas distribution. It's very turbulent, messy. There's inflow along the along filamentary directions. Here is already a rotation-supported gas disk form. This is the metallicity field. You see a relatively large enrichment of much of the volume. And around this time is sort of the heyday of this galaxy formation, sets in at redshift 2-ish or so, and these disks are resilient to some mergers. I mean, if it's not too big. It's also realization that in the past it was also thought that mergers necessarily destroy disks, but these hydro simulations are regrowing disks if there's not enough gas around fairly quickly, unless the merger is very large. And you see that things quiet down now. Here's the star formation rate, and you get at the end, a nice little disk galaxy that keeps rotating for a while. And you also notice that the evolution has noticeably quieted down. These disks spend a couple of gigayears then in sort of secular evolution at the end and still grow in mass. What's interesting, so I just want to very quickly guide you through some key results. So these cosmological simulations are now able to match a pretty large amount of data. I give you just a few examples. Here is the color distribution, which the TNG simulation for the first time matches with this accuracy. So you reproduce basically the bimodal color distribution seen in Sloan Digital Sky Survey, and this is matched nicely as for different stellar mass spins. And the appearance of this red sequence is a feature here of the HN feedback. So the one key physics prescription that was modified going to this next generation Elastic simulation was actually modeling of supermassive black holes and their feedback impacts. And we rely on that very much to produce quenched galaxies. So this is entirely in the TNG calculations something that comes about from the modeling of the black hole physics and the kinetic feedback prescription that we adopted here to produce basically, motivated by some observations of red Gazer galaxies, produce quenched systems. So that was an important first test that this kind of works. And what's also interesting, and that isn't calibrated in any way, is that the predicted galaxy populations, they matched clustering data very well. So the Sloan Digital Sky Survey is still one of the most accurate measurements of the clustering of galaxies in the present-day universe. And this is data that is really of exquisite precision. You see here the two-point correlation function of galaxies in different stellar mass spins in black dots from Sloan Digital Sky Survey, and the L bars here are smaller than the dots. So this is really very precise. And it is reassuring that these hydro simulations match in their clustering predictions what we see in SDSS without additional tuning. And this also works more or less for red and blue galaxies separately. And so the quenched systems are essentially at the right place and they have roughly the right stellar masses as well. So that is encouraging for using these hydro simulations. Then for cosmological studies, you can, for example, directly predict bias of different galaxy types, or look at things like scale-dependent bias. What they also predict is that the baryonic, there are impacts of baryonic physics on the dark matter or the total matter clustering. This is shown in this diagram. It's a comparison between the matter power spectrum in these full physics hydro simulations relative to equivalent dark matter only simulations where the baryons are also represented by dark matter. And in this comparison plot from Kisari, actually also our TNG results are included, as well as other simulation projects, Illustris, Horizon AGN, OLS, and Eagle. And you see that they're universally on sort of somewhat nonlinear scales already, or multi-nonlinear scales of k around 10-ish or so. There's a huge deficit of about 20% in the matter power spectrum. And this is attributed to AGN as well. So without the AGN, you don't get this. This is because baryons are pushed out of poor galaxy clusters by black holes. And the simulation models that reproduce also the baryon fraction in these poor clusters, which are basically these models, they all predict roughly the same size of the effect. So these things are related, so it's not completely hopeless. We think that maybe there's a chance to pin down that, not to the % accuracy that you would like to in cosmology, but it is clear that, for example, the Illustris model that predicted here almost 40%, and it's because it had a too strong AGN feedback and it expelled too many baryons out of these halos, and then the effect was overall too large. Here's a result from analysis from Shai, looking at the galaxy sizes in TNG. This is something that didn't used to work in previous calculations, but now these models also basically get the right stellar masses and the right sizes of galaxies, which is quite nice. In fact, even the morphological indicators, if you look in this plane of Gini coefficient versus M20, this is some concentration measure, then you get fairly decent agreement in the morphological properties in detail between something like Illustris and Pensta. So that's a non-trivial, I think, success, but one shouldn't be carried away too much by this, but rather focus on the more interesting sort of predictions that are maybe discrepant with data. Here's sort of one, for example, this is a sort of velocity decomposition of, again, Milky Way-sized galaxies here stacked from TNG, and the total matter profile gives you this nice flat rotation curve, which matches data points reasonably well, the dark matter. But what's then quite different between mass models for the Milky Way, here one from Bovie and Riggs, which is here I think this is the stars that Bovie and Riggs predict here up there, and the dark matter here. But the dark matter that we find in the simulations, you see, is much more concentrated. So the galaxies are dominated by dark matter all the way in, basically, almost. And that is not what many of the mass modelers for the Milky Way infer. So there's a really very substantial discrepancy, and a similar type of problem has been reported by Reinhard Genzel for higher redshift galaxies, dark matter deficient galaxies. We have to see what to make out of that. But these calculations, they predict, adiabatically contracted dark matter halos for the most part, and that is one of the interesting challenges. Here's another success in the metal profiles, but I don't want to stress the successes now more, but come to some other things, newer things on the magnetic field amplifications. But first, let me make one thing. Of course, there is the question of what you put in is what you get out. So some properties are not predictions; they are just confirmations of your tuning. And in the TNG model, this is basically the stellar mass function, which you see here, because we developed the feedback models to get the stellar masses sufficiently down and onto the abundance matching diagram to basically come out with a sensible luminosity function of galaxies. So that is not surprising that this works in the end. We worked really hard to make the black holes in particular being able to quench these galaxies sufficiently strongly. And likewise, since I mentioned the gas fractions in the TNG system, in the TNG models, we made sure that the gas fraction in poor galaxy clusters comes about right, because that was a main failure in our older calculations. And so that is, in that sense, something that we looked at in the calibration. And it's not surprising that it comes out right. And that, as I said, this also tells you that the 20% suppression in the power spectrum is what you expect from this size of baryon expulsion. Here is some words on numerical convergence. Remains a big challenge in these calculations. But because we have a sequence of simulations, we can actually use that to interpolate to sort of the result you expect for an infinite resolution. And that's something that we can do almost for any quantity. We can, study the resolution impacts over a very wide range in dynamic range, and then predict the continuum result, if you want, for fiducial infinite resolution. And for some things, this works very well. So you can also get nominal convergence for large systems. It's very hard, for example, are things like the stellar disk height in disk galaxies. It's numerically very hard to get full convergence. You see here, for example, a resolution test where that clearly shows that you get thinner disks, the better the resolution becomes. So there are effects like disk heating. Those are which is often mistakenly attributed to the gravitational softening length. And that is not the primary impact here. It's really the particle number, or rather the mass resolution that we're having.
Sorry, Volker, if you're going to, you can just go back. You're getting higher, bigger scale heights at higher resolution, it looks like, when you have smaller gravitational softening?
Yes, that's because, yes, that's true. Yeah. It's more heating here. It's two-body heating or something of that nature. Yeah. It's almost constant. I mean, I would actually say there's probably a tiny trend, but it's almost flat, I would say. But there is a sense of a slightly stronger heating. Yeah. But let me come to predictions from the simulations. That's what I find, and I give you a few examples of maybe some unexpected things. For example, here's one that shows a correlation between the disk scale length of these galaxies and the black hole size or growth. And that, in a sense, you could interpret it so the bigger the black hole is, the shorter the disk scale length on average. That probably shows that the recent growth of the black hole has an impact on the amount of the disk growth you see because of the heating impact of the black hole. We also have added magnetic fields in these simulations. So here's let me just show you a short movie. This is a small section from one of the TNG 100. It's the TNG 100 simulation, and it's a bit bright here, but you probably see this filamentary structure, and what's actually colored here is now magnetic field strength. And when you consider one of these halos, you'll see that it's actually moving, and the inflow here is driving turbulence in the system, and this turbulence, as I show you now, is a main factor in amplifying magnetic fields through a small-scale turbulent dynamo. And this is something we have studied a bit. So we looked at magnetic field amplification in some of these halos, and we think we find a very strong amplification of the magnetic field to microgauss strengths in the center. You see in the velocity field here, Kolmogorov turbulent cascade, and then consensive small-scale dynamo that brings up the magnetic field rather quickly, first in the center and then later out in the galaxies. And the fields that we then end up with, they are close to equipartition. These are two examples. Here's a comparison to a Faraday rotation map of M51. So they statistically are actually fairly consistent. And if you look at full sky Faraday rotation maps of some of our simulated galaxies, this is now actually from Auriga, which are zoom simulations with a model of Milky Way sized systems with basically the same code that's used in TNG. It's only a small difference in the black hole model, which is not very relevant for Milky Way sized systems. And you see that, by eye, these Faraday rotation maps are actually looking stunningly similar. And also magnetic field profiles. Here are some comparisons between radial magnetic field profiles in blue with typical profiles in disk galaxies. They get, you get up to B fields that are very reasonable. And then the dynamo saturates when you are at some fraction of equipartition typically. And just as a this sort of magnetic amplification you see also in very other contexts. Here I want to just show you as a sort of parenthetical remark, the side project which I was involved in, where we applied the Reaper code to the problem of stellar mergers of the two massive main sequence stars. And so basically these stars here get into contact, and this is a 9 solar mass and an 8 solar mass star. And then during the merge, eventually the nine solar mass stars funnels material onto the surface of the 8 solar mass stars, and then very quickly these systems merge, make a more massive star. Then, this is for a couple of days here, 10 days, and then it will still take 1,000 years or so until this this star sheds some further mass and returns to thermal equilibrium. But what's interesting is that look at the magnetic field during this evolution. So this is the same merger now, and what you see here is that from this material that streams onto the smaller star, there's actually an MRI instability creating a strong turbulent flow, which very rapidly, via again a small-scale turbulent dynamo in this MRI-driven turbulence, amplifies the magnetic field. In this case, in the remnant star, to about 10 to the 7 Gauss. And that's interesting because this is roughly the magnetic field strengths that you observe in so-called magnetic massive stars, which are appearing often as blue stragglers. And it's a mystery where this magnetic field strength comes from. And the simulation shows it could very well be generated by just the plain merger of two of these massive stars, and the frequency of the expected merger frequency matches the frequency of these massive these blue stragglers, basically in the galaxy. And if they then collapse, may co-collapse sometime later, the flux is conserved. It will be amplified by 1 billion times to about 10 to the 16 Gauss or so, and get a neutron star with 10 to the 16 Gauss, a magnetar. So that would be a channel to maybe make magnetars. And here you basically saw that the Arepo code, which is this moving mesh code, is particularly good at advecting, rapidly, if needed, materials through space. And this is what's relevant in this particular calculation. Another type of application here would, for example, be the tidal disruption of stars in the field of a black hole, where we also applied this code and got some quite interesting results. So let me now turn maybe a bit to some trends for the future and say something about that as well. So here is a diagram that shows the current sort of field, in a way, many of the famous simulation projects in one common diagram, in axis where we have the number of simulated galaxies and the baryonic mass resolution on the vertical and you can basically identify here two different kind of strategic directions where you can push for. You can either go for 1 or 2 galaxies or a few and invest your time in upping the resolution very much. These are the so-called zoom projects like FIRE or RIGA. They achieve the best resolution typically, of course. And then you have the classic cosmological boxes that go sort of horizontally to large volumes, and they are naturally poor in resolution. And with TNG50, we kind of try to push sort of into the diagonal, compromising on the volume, but still having a very good mass resolution, so kind of trying to achieve the mass resolution that's typically only reached in the zoom calculations, but then still having hundreds of systems, so you can then make statistics and you can understand sort of the full population mix still at some level, which is additionally the problem if you just focus on a single system. It's then often very hard to tell, is it a peculiar galaxy or is it typical? That is what systems like, simulations like TNG50 can do. But despite of all these nice successes, I think one central problem that's of course not resolved in TNG50 is, what is the physics that regulates star formation in the center, and in particular, what's the physics that expels some of the baryons out of the halo? Because we know lambda CDM can only create a successful galaxy luminosity function if many halos get rid of a substantial fraction of their baryons. And how this is accomplished is kind of hard to understand in detail, and we're using wind models that are basically put in by hand, tuned to some observations and tuned to the desired outcome as well. And what the question is in the future, what do we do about this problem? How do we make progress? And the different types of ideas around, and currently a lot of interest is invested basically on the circumgalactic medium here, because this is lower density gas, gas that we can potentially simulate ab initio reasonably well. And here you have interactions of flows that come in and winds that come out, and you have also observational ways to probe the state of this gas and its temperature, its density structure, and so on, its metallicity content. So that's something that we are trying to do, and also improve our simulation predictions. And one thing we realize is that, and other groups too, that you can, with the adaptive resolution of the mesh codes, try, for example, to place the resolution in the CGM directly and resolve that better. Not like traditionally it's done, having just a Lagrangian resolution criterion. And so the idea is basically to relatively cheaply up the resolution in this region without changing anything in the very dense phase, which anyhow, it's still harder to understand. So several groups pursue this idea to study the CGM with this improved resolution. And if you do this, one interesting thing, we can also do this with the magnetic field. So you see here one of these calculations with improved CGM resolution. In the left is the magnetic field structure, in the right is the metallicity, and the velocity field is overlaid. I'm not sure you can make this out. Maybe in the front row there are these striations here. This is actually the velocity field, and similar here you see the B field, vector field overlaid in this image. And what we found, for example, interestingly, is that the B field is actually amplified strongly and quickly in the disk of the galaxy by the small-scale dynamo there, but we also see that the B field in the CGM is coming partially from the center, and it's expelled along with the winds and also along with the metals. That's why there is a strong correlation at high redshift between the metallicity, basically per voxel, per volume element, and the B field, which at late times gets washed out, because at late times we then see also a turbulent small-scale dynamo operating in the CGM itself. So we can prove this by looking at the power spectrum again of the velocity field and the B field, and it follows the theory of a subsonic turbulent dynamo relatively well. So that's, I think, what happens. And that brings up the B field at the end to roughly uniform strength in the CGM. It's highly turbulent field. It's, however, ordered partially by some of these winds. Nowhere, however, it is dynamically important. So if you look at the plasma beta, you get basically values around 10 or so for most of the CGM. So it's an interesting thing, but it's not dynamically important. But it will play a role, and I come to this now in the context of cosmic rays. So the non-thermal particle populations are a very popular idea to maybe have a physics, a means to drive galactic winds and outflows. And unfortunately, simulating a non-thermal particle population cosmic rays, that's a really a multi-scale problem par excellence, right? Because if you look at the Milky Way galaxy disk of a size of, say, 10 to the 4 parsec, but the gyro orbit of a GeV cosmic ray, which is sort of dominating the pressure, this is at the level of 10 to the minus 6 parsec. So, this is 10 orders of magnitude smaller. So right away, you cannot do the real plasma physics of, following the individual protons around in a kinetic model. This is, of course, not possible. So you have to come up with more simplified prescriptions, and there are all sorts of two-fluid models that people propose where the plasma physics of the cosmic ray transport is simplified, approximated as a fluid that's coupled tightly to the magnetic field evolution through the gyration and the scattering of the cosmic ray particles on the magnetic field irregularities. So that's what needs to be developed, an effective two-fluid theory, ideally also taking account of the spectral representation of the cosmic ray population, which is another dimension which is making this very nasty numerically. Spare you some of the equations, but show you some of the results that motivated this. Salim, Greg Pines, and I think a student of Greg, is it a student of you? Greg? Yes. Yeah. Anyhow, this was one of the very nice initial papers showing that you get very strong cosmic ray-driven outflows, and that work, other groups also chimed in and showed that once you add cosmic ray physics, you get actually nicely cosmic ray-driven winds, bipolar outflows from this galaxy. Exactly what we want, and that happens because the cosmic rays are having a relativistic equation state. There's the Park instability, field lines open up into the halo, they can stream out into the halo, and as the cosmic ray fluid goes to lower density, the pressure doesn't decay away as fast because of the 4/3 adiabatic index compared to the 5/3 of the thermal gas. And so once you have a composite of a thermal gas and a cosmic ray, partially pressurized by cosmic rays. Once you moved it to lower density, you quickly become cosmic ray dominated. Turns out also the dissipation process in cosmic rays are slower than the cooling losses. So the energy stored in cosmic rays stays around. And you can set up a cosmic ray pressure gradient in the halo to drive these winds. So it's a very nice idea. And the cosmic ray origin is, of course, in supernova explosions. So they are believed to transform at least 10% or so of the original energy will appear first in cosmic rays. So you have a clear source. You have clear physics that could drive wind. And so that's why people pursue this. And if you study that as a function of halo mass, you find that the wind strength you're getting is modulated with the halo mass in an interesting way. The mass loading strongly increases towards lower mass halos. That's exactly the type of scaling we put in by hand, normally in our models. So here you have it kind of naturally appearing from the physics. Likewise, the energy loading of these cosmic ray-driven winds is basically constant across halo mass. Also, the standard assumption that's made in the successful wind model. So looks like a drop-in replacement for the by hand driving of the winds. Now, unfortunately, so far at least, our current attempts to make this work also in cosmological simulations are produce quite mixed results. This is sort of our most recent one. Here is a Milky Way-sized galaxy simulated sort of in our classic way, where we don't have cosmic ray physics included. And then 3 different cosmic ray models here with different transport processes, and that's sort of the crux of the cosmic ray physics. We don't really know very well how the underlying plasma physics needs to be simplified into an effective diffusion coefficient, or also effective, or it should be take streaming into account, or a mix of diffusion and streaming, or should the alphane heating be included, and so on. So basically that coupling is unclear. And the outcome now for these disk galaxies depends sensitively on what you assume for the transport processes. Here, for example, you see that for just another sort of diffusion or advection, when the disks look very different, they have the same stellar mass, but suddenly they're very, very small, don't have the right scale size anymore, don't have the right rotation curve. It's better if dissipation processes are included, so-called alphane cooling. This takes account of the fact that the streaming cosmic rays along the magnetic field lines, they will excite alphane way via the streaming instabilities, basically wiggles on the field lines on which they scatter, and that's in the streaming case, it's a loss process for the cosmic ray, and likewise a heating of the background. And in that case, if then you get at least kind of a decent disk system, somewhat smaller, so that might be okay. And we think that the reason why these disk galaxies are now very different is because the CGM structure changes very, very much. The cosmic ray pressure in the halo modifies the inflow, prevents the galaxy from growing nicely by the sort of the cold inflows coming in from the side. They are basically prevented to a certain degree, and this change of the flow pattern, the CGM, I think, is the reason why these 2 cosmic ray models in the end don't make a large disk anymore, even though the stellar mass is still okay. But all these calculations, we're still using a very simplified treatment of the interstellar medium. What we really need to do is to go to fully resolved models of the interstellar medium. This is one attempt that we currently have, the so-called Smuggle model, led by Marinacci here in this first introductory paper. You see now that this is a real multi-phase structure. This is very similar to approaches like the FIRE consortium, for example. So I think this is basically a model of very similar style and with similar residual uncertainties, and for hopefully similar successes and failures. We'll see. And just for comparison, I show you here. This is from 2000. This is the Springel and Hörnquist subgrid treatment of the ISM, a model from 2003 by now, still in use a lot. What you see the difference here is that here the fragmentation is prevented by an explicit subgrid model that's pressurizing the ISM. You still get a disk system here, and you also get a star formation rate by design that matches the observation data. So if you're only looking at the evolution of, say, the star formation rate of such a galaxy model, it's a function of time, you see that the smuggle result, which is the resolved interstellar medium, is somewhat more noisy because you have all these individual star clusters forming and the individual supernova explosions, and this smooth model produces a perfectly smooth star formation rate, which is, however, the same, on average. The stellar mass the same, the size the same, but the ISM subgrid structure is totally different, right? So it's put under the rug with the subgrid treatment. And now it depends on what you want to achieve, of course, whether such a simplified model is still good enough. I think it was good enough for a long time, but not anymore. We need to do better, and we need to improve also in other aspects. For example, we need to improve radiation fields. Here's an attempt by Rosdahl to do this. It's also very much debated whether we, for example, how you precisely should model, say, in less galactic scales, effects from radiative, for example, especially dust effects and radiation pressure on dust, which is found here in these models to basically no role in the end on these scales. We also have now finally an RT solver in our code, which we're trying to apply now to models of cosmic ionization. This is a moment-based technique, which is reasonably fast. So stay tuned for results with our recurrence implementation of our REP-RT, which is a moment-based full radiative transfer solver, which we can run in large volumes and also for isolated galaxies. That's one thing we want to work on now. And of course, to do these calculations, I just want to make a pitch that really it requires to also invest time on working on more accurate and scalable codes. That is not a very popular direction to go normally, but somebody, I think, has to bite the bullet. And since this is the Center for Computational Astrophysics, I felt I'm allowed to make a pitch to that this is also worthwhile and interesting. So we are, for example, Rainer Weinberger helped me to make the repo code public, at least in the basic version. So we have this code, and the real code is about 335,000 lines. You see, this is a many years of investment. You can only produce this and maintain and improve with large teams. And this public code was cleaned up to much more manageable base. And we'll soon have a new code, Gadget 4, which is revised in its code base and hopefully much cleaner and has some interesting options. So that should come out soonish as well. But maybe one should also sometimes think, maybe going back to the drawing board and think about the mathematics that's behind the methods. And here, for example, if you talk to an applied mathematician about how should you solve the Euler equations, they will typically tell you should use discontinuous Galerkian methods. And so this is the hyperbolic system of ideal hydrodynamics, and instead of using the standard sort of finite volume schemes that are used with reconstruction techniques, and you can also convert this to a weak formulation of this PDE, and you then basically represent in every resolution element, which can be a cube, but could also be a triangle or any other different geometric shape. You basically use the finite element method. You expand the solution inside this element into a basis. Legendre polynomials, for example, are popular, and then you evolve through this equation. You evolve via flux computations and internal integrations for some Gauss points through this volume. You evolve the expansion coefficients directly, and you're not throwing away the values after time step. That's done in the normal finite value methods, but you're keeping them, and that gives you a much higher computation efficiency. And then if you look at the same number of degrees of freedom, the question is, for example, if you suppose you want to approximate this solution here, the dashed line, numerically through some discretization scheme, you can do this in a piecewise constant way. This would be this red approach here with a certain number of degrees of freedom at zeroth order. At first order, you would make a piecewise linear, piecewise parabolic, and then you have a cubic quartic polynomial here. And you see now you have only 3 bins here, 3 resolution elements, but you have a higher order representation of the solution. And this solution here is, or this purple line, approximates what you want much better, even though you have the same storage requirement and the same number of degrees of freedom. And that's just an illustration that maybe going to these higher order schemes does give you higher accuracy for cheaper computation effort. And this is indeed true. You can show these higher order methods are faster than, say, finite volume methods at second order, and they very easily generalize to higher order. So DG, we have this also in MHD to 7th order now on an adaptive Cartesian grid in one variant of our code. And you can then show for certain types of problems, you get higher accuracy for given investment of CPU. Right? And so the question then will be in the future whether you can really apply that to astronomical problems of interest. Because one thing is, and that's what we learned, is that these higher order discontinuous Galerkin methods, they are really very neat and fast and accurate. And they are like tuned Formula One race cars, and these are very fragile action machineries, right? So they, if you hit them a little bit, they don't work properly anymore. And what we sometimes basically need is codes that make their way through the mud, right? And that's why we're currently uncertain whether we can get these higher order methods, which for smooth problems are definitely the way to go. For example, if you want to study just driven turbulence, it's one of the disciplines where these models these codes are really shining, and they're declassifying basically finite volume methods in terms of efficiency and accuracy. There you can apply them, but in a messy TNG-like simulation, you need also source terms that are discretized at higher order, otherwise including the self-gravity. That's a problem we haven't really solved yet, and that's why we currently can't use that. And the other thing that's always needs to be done is to scale the codes to very large processor numbers. That's something that is here just a work in progress here for a weak scaling plot for the Gadget 4 code, where you see that here we go up to 50,000 cores, and it works perfectly in the 3 gravity, not so perfectly in the long-range PM gravity, but overall decently. So this is sort of the work we need to do, because the exascale systems that are coming, also in the US, they of course, there you have to exploit concurrency going not only to 10 to the 5 processing elements, but 10 to the 6, that's 10 to the 7 or beyond that. And that's, I think, it's going to be very hard to do this for any interesting problem in cosmology. And you have to adopt GPU computing as well. So let me just give you some take-home points. So I try to give you a bit of a tour of the history of hydrodynamical simulation of galaxy formation, lambda CDM. So they are actually stunningly successful, I'd say. I was very desperate for a while to make a disk galaxy 10 years ago. I was very desperate, but now suddenly we get them. They do work really stunningly well, but it shouldn't hide, or the new challenge now is, of course, to do what we parameterize the small scale physics better. That's a multi-scale, multi-physics problem. I think simulations will be very much necessary to eventually nail it. And I should say that that's where the small collaboration here is exactly addressing this challenge, how to link the different understanding and models and codes we have from very tiny scales of individual stars and their explosion of supernova all the way up basically to the whole universe. And that's a challenge at the moment. But I'm after this meeting also here the last days, I'm actually quite uplifted that this eventually will be possible with all you guys. Thanks a lot.
Excellent talk, Volker. Now we can take some questions. Ed Drummond.
Yeah, really excellent talk. Thank you for that overview. You talked some about the small-scale dynamo in the ISM and in the CGM, and then you showed a comparison of Smuggle and a similar galaxy using the Springel and Hernquist model. Now, that much smoother ISM using Springel and Hernquist, I presume, is a less efficient, or it changes the small-scale dynamo. I wonder if you can say anything about the resulting magnetic field strength when you start to resolve the phase structure a little more.
Yeah, it is true. You're absolutely right that with the smooth model, you will kill part of the you kill much of the small-scale dynamo in the interstellar medium itself. We still get a strong amplification in this case, but we think it's slowed down substantially. The issue is the small-scale dynamo, if it's really operating, it is driven by the smallest eddy turnover type scales, which are very, very short. So you then get exponential growth on basically tens of mega years or 100 mega years. And so once this kicks in, there's the field strengths. We start with a tiny 10 to the minus 14 Gauss seed field. You could seed it also from stars or Biermann batteries or so. We put this in by hand at the moment, but this is then picked up, and the field is exploding in a few hundred mega years up to saturation, right? And what I think we're getting wrong basically with this smooth model is that we're actually seeing the amplification even too late. But the final state, we think, is fairly similar. Or the final field strength is just basically given by the saturation point when the magnetic forces become important, relative of comparable size to the thermal pressure gradients. And that's always the same. And that's also why I think we get the final field strength roughly correct, because we sort of get the right pressure in the interstellar medium, and then that setting ultimately at the B field strength, so you basically end up with something of order equipartition. It's a bit more complicated because of rotation, but still it's close to equipartition. It's a bit weaker than that. Yeah. So, but you're right. I mean, I'm not saying that we're getting the magnetic field amplification correct. We know that the speed of which we also with resolution, with a high resolution at cosmological scales, so this typically starts at high redshift already in the turbulent flows. And if you have higher resolution, the amplification starts earlier, it's faster because we have smaller scales resolved. Final field is the same though.
Thank you.
So you showed this deviation from the Boolean Ricks.
Yeah.
Do you, in our galaxy, the bar plays a significant role in its dynamics, and it's probably scatters dark matter. The bar-dark matter interaction is happening through pretty high order resonances.
Mm-hmm.
Do you think the numerical codes right now have the resolution that they're properly capturing what's going on dynamically with things like bars on the kiloparsec scale?
I think so. They're beginning to do that. So that's also a new development, that you can do real credible galactic dynamics with cosmological simulations. That's a new development. I think it's somewhat borderline, but certainly bars and the pattern speed of bars and so on, you can start to predict, I think, in a reasonable, credible way with the best cosmological simulations. So like the best fire ones or the best Auriga ones are able to, I would say, run so that maybe not all the nitty-gritty details of spiral arm dynamics and so on, that I would not think is possible yet, but bars and pattern speeds and are possible, I think.
But dynamical friction, because the bar, the bar halo interactions are pretty important there.
Yeah, that's right.
I mean, I have this very old prejudice from visiting Mars and Santa Cruz and looking at orbits in the, in the models and watching box orbits code the loop orbits and back and forth. This is many generations ago. But but it's a very demanding problem to get right at this.
Yes, and the resonances are very sharp and so on, and I think, especially if you have very symmetric potentials. On the other hand, for example, the pattern speeds of bars, now we for the first time seen Auriga, the correct pattern speeds of bars and robustly with resolution. So that's a measure, but some of the resonant phenomena, it's possible, I agree, that we still wash this out in our in-body noise. But however, I would now say, because traditionally lots of the galactic dynamic studies have used toy simulations to get the particle number up high enough and so on, and that makes a number of simplifications that are maybe not, that are, for example, no substructures that is flying around all the time, no e-fall, no satellites, no asymmetries, no tidal fields from surrounding structures, and all of that you get for free in the cosmological case. And so I think now, if I was purely interested in the system, in the galactic dynamic problem, I would try to push the resolution further in the galactic case, because I think that's the much more promising way. With the isolated toy studies, you have so many arbitrariness in the initial conditions. That's the key advantage of the cosmological simulation. There's no freedom in how you get to your system. It's numerical parameters, okay, in terms of resolution, but other than that, while in the isolated case, the whole structure and even the initial conditions depend sensitively on how you construct your distribution function for the disk and so on, how stable it is, and that's coming for free. That's why I believe that galactic dynamic studies are better off turning to the cosmological simulations now.
Volker, going back to your simulation of the merger of two massive stars, very interesting results. So one of the big challenges is to, when explain magnetized massive stars, is to show that the magnetic field is in a stable configuration. So I believe at the end of your simulation, you're showing mostly the toroidal component of the field. And so that's unstable to the Taylor instability. And I'm wondering if you can comment on what you think will be the longer-term evolution of the magnetic field from your snapshot of your simulation.
Yeah, as you probably are aware, we haven't tackled that. We cut off the calculation in 3D after like 10 days or so, and then mapped this to a one-dimensional stellar evolution calculation. And that mapping and also the viscous evolution of this torus is very unclear. And I'm not sure what I mean, I guess my honest answer is I'm not really sure what dynamic is going to happen, how this system will settle down, how much mass it will shed.
If you have something to say about the colloidal, if you have a large-scale colloidal component of the field that emerge in the simulation, usually you will need the colloidal and the toroidal to be interlocked somehow, so that the field will relax to a stable configuration.
Yeah, but that's, I mean, a dynamical from the MHD point of view, I think it's a very interesting problem, and also what type of reconnection effects you might have there and so on. So I really, except for giving the lame answer that we need to now run this longer, I cannot really say. I'm not an expert enough on these isolated stars. You know, this is sort of, as you probably know, you are the expert on that. So
that's why I asked the question.
Yeah.
Piqued his interest.
About galaxies.
We were just
it's like galaxies. So maybe one additional question?
I wanted to know your opinion. So, let's say that you have a graduate student these days, but he has to do some massive calculation. Will you recommend that he write the code for a GPU, or still doing like a standard code where you can run with CPUs, thinking in 10 years time or something like this?
Yeah, and unfortunately, I mean, a student who loves coding and is capable of doing this with his or her left arm, I would say yes to GPU computing, because I think the reality is that at least depends on where you want to go with computing. If you're into high performance computing and you think you're going to use the exascale systems that's going to be here in a couple of years' time, then you need to invest in GPU computing, because at the moment it looks like that all the machines in the US and also in Europe will be GPU accelerated, and it's which is really bad news, I think, for in terms of, because it means you have to address this technical challenge to get performance on this, and that is not trivial. It depends very much on the code or the type of problem. There's some problems that are easier than others, and yeah, I mean, machine learning you can do well on GPUs since you do this. But I think tightly coupled problems and our codes tend to, for example, this Voronoi mesh, this adaptive mesh, is just horrible because it has too many if conditions, branches all the time, and that's not very good for GPUs. So a structured Cartesian hydrocode, people have written very nicely, highly efficient codes, and Jim Stone is quite far. Well, they're also tackling with this. Even Jim Stone needs to invest very serious work to get Athena++, to work very well on GPUs. And on structured grids, however, you can at least you're in a better starting position than with this unstructured mesh. So that's, by the way, also one reason why we're thinking this DG method is potentially interesting. There we go back to Cartesian, adaptive Cartesian meshes. They map more easily on GPUs. And radiative transfer is also one of these very expensive problems that can be done on GPUs. And yeah, I think you have to get a black belt in all the numerical methods, ideally, then you're in business. Yeah. So. But not everybody needs to do that, of course. It's enough if some people do it, but somebody has to tackle it. Otherwise, we leave these machines to the material science people or other boring applications.
Can't have that.
With that, please join me in thanking Volker again.